Tonight, we drift quietly through the silent depths of the Milky Way. Across an endless sea of stars, we glide through a universe woven from the light of thousands of suns. Here, every star, every cloud of dust, every hidden current of energy tells a story shaped over billions of years. Close your eyes and imagine yourself as a particle drifting through the galaxy's vast expanse. Pale starlight filters through ancient clouds, shimmering softly. Massive star clusters and hidden flows of energy perform a silent dance across the void. The Milky Way is a labyrinth of secrets shaped beyond time itself. Every corner whispers quiet curiosity awaiting to be discovered. On this cosmic journey, release your thoughts, step away from the day-to-day, and simply attune to the rhythm of the universe. Light takes hundreds of thousands of years to cross the galaxy. Consider the limits of speed. Compared to a beam of light in a room, the galaxy's enormity challenges the imagination. Space between stars is not empty, yet light passes gently, weaving between atoms and dust particles. Each fragment carries its own melody in the galaxy's silent symphony. When we gaze at the Milky Way, we are not seeing it as it is now, but as it was long ago. Layers of cosmic history, stretched across unimaginable distances, unfold before our eyes. Light from distant regions began its journey long before humanity existed, and every faint shimmer in the sky carries a fragment of ancient time. Even the fastest thing in the universe appears gentle and deliberate on a cosmic scale. At the heart of our galaxy lies a supermassive black hole, invisible yet shaping the motion of stars and clouds of gas, quietly guiding the galactic dance. Around this hidden giant, stars and clouds of dust trace spiraling paths at incredible speeds, responding to the unseen pull of its gravity. Near the core, the force becomes overwhelming. Farther out, it exerts a subtle, elegant influence. Gas clouds stretch, twist, and spiral inward, heating and glowing as they fall toward the dark center. The black hole itself is silent, but its surroundings vibrate with the motion of infalling matter. This secret heart stabilizes the galaxy, gives shape to its rotation, and weaves invisible threads connecting its stars. Imagining a force capable of bending space without light or sound inspires awe. The galactic core is not a calm sanctuary, it is a restless domain ruled by an unseen giant. Deep in history, the Milky Way once devoured a companion galaxy nearly half its size. The tidal forces of that ancient encounter gradually tore it apart, leaving echoes that continue to shape the galaxy we see today. Stars, clusters, and streams of cosmic debris have been gradually absorbed by the Milky Way's immense gravity, shaping the galaxy we see today. The traces of these ancient mergers appear as energetic stars and broad, sweeping flows of stellar material, remnants of systems long gone. Astronomers can still identify these fragments by their unusual motions and distinctive chemical fingerprints, different from stars born within the Milky Way itself. These cosmic encounters thickened the galactic disk, stirred the dark matter halo, and influenced the formation of spiral arms. Large galaxies do not grow through sudden events alone. They evolve through countless subtle interactions spanning unimaginable stretches of time. The Milky Way carries the echoes of these ancient companions, now integrated as ghostly stars shining within our own celestial home. Our galaxy is surrounded by dozens of ancient satellite galaxies. These silent companions drift along long, elegant orbits, sometimes blending almost entirely into the surrounding darkness. They are often old and sparsely populated, delicate in appearance, yet vital to the evolution of the Milky Way. Their slow passages create ripples in the outer halo, and some have already begun forming faint stellar streams, leaving wisps of pale traces that encircle the galaxy like ancient threads. The sun, too, rides this grand cosmic dance, moving far faster than it appears from our perspective on Earth. Though it may seem like a stable anchor in the sky, it travels faster than a bullet, carrying the entire solar system along with it. Every planet, every moon, every drifting speck of dust participates in this vast journey. Guided by gravity and shaped by the collective mass of countless stars, the Sun traces a curved orbit around the galactic center, following a complex path through the galaxy's immense structure. Even if we cannot feel it, the solar system is in constant motion. This journey shapes its distant future and determines the paths we follow through different regions of the Milky Way. Along the way, we encounter delicate gas clouds, faint radiation zones, and subtle currents of gravity. This quiet voyage has persisted for billions of years and will continue for billions more. The idea alone inspires awe. Our familiar star, a traveler on a vast galactic orbit. Stars are born in clouds colder than anything on Earth, where fire cannot exist. Most imagine stellar birth as a burst of light and energy, yet reality begins in profound silence. Dust and gas clouds in the Milky Way block starlight, appearing dark to our eyes. Molecules drift slowly, and temperatures are impossibly low for flames. Gravity gently gathers the cold matter, forming dense pockets. As these pockets grow heavier, they collapse further, and their cores gradually heat up. Over eons, temperatures rise until nuclear fusion ignites, transforming a dark, cold cloud into a shining star. This process reminds us that creation often begins in stillness and quiet. Our solar system drifts within a vast bubble carved by ancient stellar explosions. Long before humanity, massive stars lived fast and ended in explosive deaths, sweeping away surrounding gas and creating a spacious, airy cavity. Within this bubble, filled with thin, heated gas, our sun and planets move gently, gliding through the quiet remnants of violent past events. The bubble's edges are shaped by cooler walls of gas formed from explosion debris. Astronomers map this structure by observing the faint light emitted by the gas, recognizing that our entire solar system resides within the remnants of stars long gone, offers a humble and profound perspective on the universe. We are surrounded by the silent echoes of ancient cosmic events that shaped the space we call home. Over time, the Milky Way gradually draws smaller galaxies into itself. From afar, galaxies may appear calm and still, yet over billions of years they interact, merge, and evolve. The Milky Way is no exception. A few nearby satellites are slowly being pulled into its vast orbit. As these galaxies disintegrate, their stars stretch into long, delicate streams, weaving through our galaxy. Gradually, these stars become part of the Milky Way, carrying the history of ancient mergers and helping shape its structure. This quiet, persistent consumption explains the presence of dispersed star clusters and unusual stellar populations across the galaxy. Even now, faint companions like the Sagittarius dwarf galaxy are being torn apart as they spiral inward. Some of the stars in our galaxy are more than twice as old as Earth, offering a glimpse into the Milky Way's earliest days. These ancient suns bear chemical signatures of the early universe. Formed before heavier elements were abundant, their atmospheres are simple, their light subdued, and their stories stretch across millennia. Many of these aged stars drift through the sparse galactic halo, far above the spiral arms, tracing silent, elongated orbits. Observing them allows astronomers to study the early universe in a direct and unobstructed way. These ancient suns have carried the galaxy's secrets across billions of years of quiet illumination. On a clear night, these stars collectively form the luminous band we recognize as the Milky Way. Most are too faint to distinguish individually, yet in immense numbers they provide a soft backdrop that fills the galactic disk. Dust and gas scatter their light, giving the galaxy a hazy, ethereal appearance. These faint stars are the hidden architects of the Milky Way. Their combined mass shapes the gravitational field that guides brighter stars. Some are elderly red dwarfs burning quietly, while others are young stars just beginning their journey. Together, the countless stars of the Milky Way breathe life into a vast, luminous, and living galaxy. The Milky Way is a stage filled with invisible suns and wandering stars. The light we see in the sky is not just the glow of a few bright stars, but a soft, quiet chorus of countless stars. Not all planets belong to a star. Some worlds drift freely through space without a sun. These rogue planets likely formed in star systems long ago, but were ejected by gravitational interactions. Without a sun to warm them, these worlds travel through the deep cold of the galaxy. Their surfaces may be frozen, yet they can conceal pockets of internal heat. The idea of planets wandering alone evokes a quiet, eerie beauty. They follow unpredictable paths, passing near stars, slipping between clusters, or drifting toward the galactic halo. Though hard to detect, simulations and faint observations hint at their existence. Beyond the spiral arms of the Milky Way, a halo of gas envelops the galaxy, far hotter than any flame on Earth. This galactic halo stretches above and below the disk for vast distances. The gas becomes so energized that it emits faint X-rays. Despite its tenuous nature, it possesses enough mass to influence the motion of stars and satellite galaxies. This halo is a remnant from the galaxy's early formation, carrying material expelled by supernovae, and it may one day fall back, fueling new star formation. The Milky Way is not merely a flat disk of stars. It is layered and complex, with components extending into space. This hot, quiet envelope wraps the galaxy like an ancient cloud. Echoes of ancient stellar explosions traverse the galaxy as radio waves. When a star dies in a supernova, it sends shock waves through the surrounding gas, and even after its visible light fades, the radio glow drifts silently through space. Astronomers track these faint signals with precise instruments to map remnants hidden within the dust. Each wave carries information about the explosion's energy, the shape of the expanding cloud, and the dispersed matter. These waves reveal the hidden history of star deaths that enriched the galaxy with heavy elements long before humans existed. A teaspoon of a neutron star would weigh as much as a mountain. These dense objects form when massive stars collapse after a supernova and are among the densest things in the universe. They are a quiet, yet awe-inspiring part of the Milky Way's complex structure and the life cycle of stars. Matter is compressed so intensely that ordinary atoms cannot survive. Protons and electrons merge into neutrons, creating a form of matter unlike anything on Earth. If you could hold a teaspoon of it, a feat no human could ever accomplish, it would weigh more than a mountain. This extraordinary density reshapes the behavior of light, magnetism, and gravity nearby. Neutron stars spin hundreds of times per second, emitting powerful beams of radiation into space. They generate magnetic fields far stronger than anything human technology can produce. Their surfaces are remarkably smooth, and gravity is so extreme that even a small bump cannot persist. These strange remnants cool slowly over millions of years, releasing trapped heat as they gradually fade. Scientists study them to explore the limits of matter and the conditions in which it can exist under extreme circumstances. The Milky Way is threaded with ancient stellar rivers. These streams of stars are the remnants of smaller galaxies and clusters that were once whole but gradually torn apart by the Milky Way's gravity. As they stretched, the stars dispersed along their original orbits, leaving vast trails. Faint though they may be, these streams serve as silent records of the galaxy's past interactions. By examining their shapes and motions, astronomers can reconstruct the histories of the galaxies that contributed to them. Some streams curve high above the galactic disk, while others flow quietly within it. They reveal how gravity has sculpted the Milky Way over eons, redistributing stars across immense distances. These delicate ribbons also help map the invisible dark matter surrounding the galaxy. The paths of stars trace gravitational fields, showing how unseen mass influences motion. The Milky Way is a galaxy of constant birth. Within cold, shadowed clouds scattered along its spiral arms, gravity pulls gas into dense pockets. These pockets slowly compress until their cores reach temperatures high enough to ignite nuclear fusion. That moment marks the birth of a star. Across the galaxy's vast disk, stars emerge so continuously that a new one ignites every second. The variety of newborn stars is astonishing. Some are small red dwarfs destined to burn quietly for trillions of years. Others are larger and brighter, living short, brilliant lives that end in powerful supernovae. Star-forming regions are turbulent, shaped by magnetic fields and the remnants of previous generations of stars. Each new star adds to the Milky Way's dynamic, evolving and intricate cosmic tapestry. The light from newly formed stars gradually clears the surrounding dust, revealing clusters that shine against the darker backdrop. These young stars also send out energetic winds, shaping the clouds from which they were born and influencing their surroundings. The continuous birth of stars is one of the processes that keeps the Milky Way alive and dynamic. Even as older stars fade, new sources of light constantly emerge to illuminate the galaxy. Some stars rotate at astonishing speeds, so fast that, without their own gravity, they would tear themselves apart. In the Milky Way, there are stars whose quasars move at hundreds of kilometers per second, far surpassing the sun's rotation. This rapid spin causes them to bulge outward, forming slightly flattened shapes rather than perfect spheres, and raises surface temperatures at their poles. Their rotation also generates powerful magnetic fields, which can influence the flow of surrounding gas and dust. Some of these fast-spinning stars create faintly glowing disks or rings around themselves. How they spin affects how they burn their fuel, how they evolve over time, and how they will eventually die. Observing them provides a rare glimpse into the extremes of stellar physics. Vast, empty regions exist within the galaxy. Not every part of the Milky Way is filled with stars and gas. Some areas are astonishingly sparse, carved out by ancient stellar winds and explosive supernovae. These enormous voids can stretch across hundreds of light years and form delicate pockets within the spiral arms. Over millions of years, successive explosions merge into even larger cavities. Although these regions contain fewer particles, they are still subtly influenced by the surrounding gas pressure and the galaxy's gravitational field. By studying these voids, astronomers learn how the energy from dying stars has shaped the Milky Way and how stellar clusters have affected their environments. Among the Milky Way's strange and diverse planets, some are so rich in carbon that layers resembling diamonds form deep within them. These exotic worlds likely developed in regions with carbon-rich materials, differing from areas dominated by silicon and metals. Under immense pressure, carbon crystallizes into solid, diamond-like structures. Their surfaces may be dark and rocky, but beneath lies a landscape shaped by exotic chemistry. Depending on their formation and proximity to their stars, these planets may orbit closely or drift to more distant regions of the galaxy. Studying these phenomena allows scientists to understand the wide variety of conditions present within our galaxy. They reveal that planets can differ drastically from those in our own solar system. Imagining worlds with hidden glowing layers made of carbon-rich materials evokes a quiet sense of awe. These diamond planets demonstrate that the Milky Way hosts planetary wonders far beyond anything we observe on Earth. Our galaxy contains stars capable of releasing immense bursts of energy. Some stars can suddenly erupt when their surface magnetic fields twist and snap, producing radiation so intense it could strip away the atmospheres or alter the surfaces of nearby planets. Though such events are rare, they highlight how dynamic and unpredictable stars can be. The bursts propagate through space as flashes of light and high-energy particles, detectable even across vast distances with sensitive instruments. Observing them helps astronomers probe stellar magnetism and the surrounding interstellar environment. Certain star systems in the Milky Way host dozens of planets. Young stars are surrounded by massive disks of gas and dust, which gradually coalesce into planets. These disks are often far larger and denser than the one that formed our solar system, enabling the creation of many more worlds. These planets vary in size, composition, and orbit. Some are rocky, some icy, some orbit close to their star, others drift farther away. Over time, gravitational interactions produce complex orbital patterns. Examining these systems offers astronomers valuable insight into how planets form and evolve under different conditions, revealing the remarkable diversity that can exist even within a single stellar family. Some stars are ejected from their systems entirely, set adrift on solitary journeys. In dense clusters, close encounters or companion stars' supernova explosion can fling stars from their original orbits. Once ejected, they traverse long, lonely paths across the galaxy, often moving faster than neighboring stars, drifting out of spiral arms into quieter regions. Though seemingly ordinary, their light betrays their extraordinary pasts. Studying these wandering stars helps astronomers understand the dynamics of stellar systems and the forces capable of disrupting them, offering a glimpse into the Milky Way's more chaotic epochs. In certain regions, stars are born so densely packed that their individual boundaries blur. These clusters form when vast clouds of gas collapse simultaneously into hundreds or thousands of stars. Within these clusters, stars remain close to one another for long periods before gradually dispersing. Their combined light creates a radiant glow that fills the surrounding space. Some clusters are spherical, with stars tightly bound toward the center, while others form looser associations that shine amidst the dusty spiral arms. Clusters provide insight into stellar evolution because even when stars are roughly the same age, differences in mass cause them to evolve at different rates. Observations show how stars grow, age, and eventually fade. Clusters also shape their environment. Their strong radiation and stellar winds carve gaps in surrounding gas, influencing where the next generation of stars will form. Stars are rarely born alone. They merge in these vibrant, moving neighborhoods of collective light. The Milky Way's molecular clouds are enormous, composed largely of cold hydrogen and dust, containing enough raw material to create thousands of stars. These dark, frigid regions are among the galaxy's quietest, yet most fertile areas. Their immense mass allows gravity to form dense knots where nuclear fusion ignites at the core. Despite their scale, molecular clouds are delicate. Radiation from nearby stars erodes surfaces, while supernova shockwaves compress gas to trigger new star formation. These clouds stretch along the spiral arms for hundreds of light years, supplying the essential ingredients for new solar systems and sustaining the galaxy's ongoing cycle of life. Some stars pulse with rhythmic brightness, almost like the heartbeat of the galaxy. Their interiors expand and contract under the influence of heat and pressure, producing cycles of light that can last hours, days, or even months. These stellar pulsations provide a window into the hidden interiors of stars, offering vital clues that cannot be observed directly. They remind us that the Milky Way is not a static collection of lights, but a dynamic living system, constantly in motion and continually evolving. By analyzing these vibrations, astronomers can determine a star's mass, age, and temperature. Some of the most well-known pulsating stars serve as cosmic distance markers, as their brightness patterns follow predictable cycles. These stars provide reliable measurements for mapping the structure of the Milky Way across vast distances. Pulsations occur in young stars, aging giants, or stars in transitional phases of their evolution, with each category exhibiting its own distinct rhythm. These gentle stellar oscillations impart a subtle sense of motion to the galaxy, reminding us that even seemingly static points of light conceal intricate internal patterns. Shock waves from ancient supernovae continue to propagate across the galaxy long after the explosion itself has faded from view. These ripples sweep through the interstellar medium, carrying the energy of the original outburst into the depths of space. As they travel, they compress gas clouds, heat the surrounding material, and leave delicate traces of their passage. Some shock waves sculpt dusty regions into new forms, while others pass through emptier areas, gradually weakening but preserving the memory of their violent origin. The full expansion of a shock wave can take tens of thousands of years, and during this time it can trigger the formation of new stars while enriching the interstellar environment with heavy elements forged in the supernova. Modern observatories detect these waves through the faint X-ray and radio emissions they produce. The shock fronts appear as expanding shells or filaments, revealing the structure of the surrounding space. Even when the dust that created them has long dispersed, their influence silently persists, shaping the environment for future generations of stars. The dust that permeates the Milky Way originates largely from the final stages of dying stars. Much of it forms in the outer layers of aging stars as they approach the end of their lives. As stars swell into red giants, their outer atmospheres cool enough to condense small, solid grains. These layers are eventually ejected, releasing dust into the galaxy. Massive stars generate additional dust when they explode as supernovae, dispersing newly created elements into the interstellar medium. Over time, these grains drift across the Milky Way, becoming essential building blocks for new stars and planetary systems. Dust cools collapsing gas clouds, shields molecules from harsh radiation, and provides surfaces for chemical reactions. By absorbing and scattering starlight, it gives the galaxy its gentle glow and shapes its nebular appearance. Each particle carries the legacy of its parent star, a delicate connection linking the ancient deaths of stars to the creation of worlds, including our own Earth. Near the galactic center, a handful of stars orbit at extraordinary speeds, far surpassing the motion of stars in the more distant spiral arms. This region is dominated by intense gravitational forces, and these rapidly moving stars trace curved paths shaped by the galaxy's concentrated mass. Their velocities were first detected by carefully monitoring their positions over many years. These tight, high-speed orbits offer compelling evidence of the complex gravitational environment near the Milky Way's core, revealing the intricate dance of stars under extreme conditions. The movements of stars allow astronomers to calculate the mass of unseen objects that govern their orbits. These stars also provide clues about the structure of the central regions, filled with complex gas clouds, intense magnetic fields, and radiation. Despite the extreme conditions, the stars themselves remain stable, quietly shining as they follow their dramatic paths. Observing them requires advanced infrared telescopes capable of peering through the thick dust surrounding the galactic core. Their speeds and precise motions reveal rare insights into one of the Milky Way's most gravitationally intense regions. In some areas of the galaxy, gravity is so strong that even starlight bends as light passes near dense regions, whether tightly packed star clusters, dark matter concentrations, or unexpectedly massive gas clouds. Its trajectory shifts slightly. This bending can magnify, distort, or alter the appearance of distant objects, a phenomenon astronomers call gravitational lensing. This effect allows the detection of otherwise invisible objects, such as freely roaming planets or dense stellar remnants hidden in dark regions. It also reveals the distribution of mass within the galaxy, showing how much is ordinary matter and how much is dark matter. The silent deflection of light reminds us that the universe is far from simple or uniform. Every beam of light reaching our eyes has been subtly shaped by the gravitational landscape it has traversed. At the same time, cosmic rays from the galaxy constantly strike Earth. These high-energy particles originate from supernovae, active stars, and turbulent magnetic fields, traveling at near light speeds across vast distances. While our planet's atmosphere and magnetic field protect us from most of them, a continuous flux still reaches us. Most of these particles are harmless, interacting with molecules in the upper atmosphere and creating showers of secondary particles that never reach the ground. Studying cosmic rays helps scientists understand energy flows across the galaxy and map magnetic structures. Though invisible, they form a persistent presence and create a quiet backdrop of activity around our planet. Some stars are so hot that the intense heat and ultraviolet radiation they emit can strip the atmospheres from nearby planets. These stars are often young or extraordinarily bright, expelling powerful winds and charged particles. A planet exposed to this constant energy gradually heats its upper atmosphere, causing gases to escape into space. Over time, this can deplete most of the atmosphere, leaving behind a barren surface. These interactions shape the evolution of planetary systems. Some planets that initially had thick atmospheres can slowly become dry and airless. Observing these effects allows astronomers to understand how stars influence the habitability of surrounding worlds and how planetary atmospheres change under different conditions. Although the process is gradual, a single star's intense energy can reshape an entire planet. These hot stars serve as a reminder that each world in the galaxy exists within a delicate balance of radiation, gravity, and atmospheric forces. The Milky Way is a dynamic environment where these forces continuously sculpt planets, creating conditions both beautiful and perilous. The Milky Way hosts magnetars, rare neutron stars with extraordinary magnetic powers. These objects possess magnetic fields far stronger than most stars, intense enough to distort atomic structures and warp the surrounding space. Occasionally, magnetars release bursts of energy so powerful that they briefly outshine nearby stars. These flares result from sudden shifts in their magnetic fields, cracking their outer layers and sending high-energy radiation across space. Though only a few kilometers in diameter, their influence can be felt across vast distances. Compared to typical neutron stars, magnetars rotate more slowly, but their magnetic might makes them unique. Studying them allows scientists to understand how matter behaves under extreme conditions, adding a layer of mystery to the Milky Way. Some planets in our galaxy orbit binary star systems rather than a single sun. These worlds trace complex paths shaped by the combined gravitational pull of two stars. The light from these stars creates extraordinary sunrises and sunsets. Sometimes both stars rise together, sometimes one sets as the other ascends. The constant shifts in light and heat produce climates unlike anything on Earth. These systems reveal the flexibility of planet formation, showing that even amidst complex stellar environments, planets can find stable orbits. Examining these arrangements helps astronomers understand how planets adapt to diverse conditions and how common such configurations may be across the Milky Way. Near the galactic center, faint antimatter clouds appear. Antimatter, which annihilates upon contact with normal matter, emits radiation detectable across space. These elusive clouds carry the signatures of extreme energy processes occurring in the galaxy's heart. Their origins remain uncertain, possibly tied to massive star activity, energetic jets near the central black hole, or interactions within dense gas clouds. Because antimatter is difficult to produce and nearly impossible to contain, its presence in the Milky Way is striking. Studying these clouds offers insights into the extraordinary conditions near the galactic core, where intense gravity, powerful magnetic fields, and frequent stellar explosions converge. The galaxy also preserves memories of vanished star systems through long tidal streams. These delicate threads of stars stretched across the Milky Way are remnants of smaller galaxies gradually torn apart by gravitational forces. As stars are dispersed by the galaxy's pull, each stream carries the unique imprint of a once independent galaxy. Astronomers can study their motions and compositions to reconstruct the histories of these lost companions, revealing the Milky Way's dynamic past. Some stellar streams twist far above the galactic plane, while others flow quietly along the spiral arms. Their shapes reveal how the Milky Way has grown over eons by assimilating smaller neighboring galaxies. These streams also trace the invisible scaffolding of dark matter, curving in response to the galaxy's unseen gravitational framework. Tidal remnants like these serve as reminders of the Milky Way's long and dynamic history, a record of countless interactions with neighboring systems, each leaving behind a faint yet elegant signature. These ancient star trails drift silently through space, carrying stories older than Earth itself. Binary star systems are a common feature of our galaxy. Many stars are not solitary, but form in pairs, performing a gravitational dance around one another that can last billions of years. Over time, some binaries spiral inward, gradually exchanging energy with stellar winds surrounding gas or tidal forces. Eventually, the two stars may collide, releasing a spectacular burst of light and energy, sometimes observed as a luminous red nova. The resulting merged star is often larger and brighter than either of its progenitors, and these mergers enrich the galaxy with heavier elements as matter mixes and heats during the event. Studying these extraordinary collisions allows astronomers to understand stellar evolution and the formation of rare cosmic objects. The idea that two stars can slowly converge and unite into one adds a poetic sense of motion to the Milky Way. The night sky of the Milky Way is serene, yet countless celestial dances unfold in ways far beyond our imagination. Some planets experience metal or glass rains. Among the thousands of worlds scattered across the galaxy, certain planets endure climates unlike anything on Earth. On extremely hot exoplanets, temperatures can soar high enough to vaporize metals. As the atmosphere cools slightly, these vapors condense into shimmering droplets that fall as metallic rain. On other planets, intense winds carry molten silicate droplets across the sky, creating roaring storms of glass that sweep laterally at incredible speeds. Surfaces of such planets may be dominated by glowing lava oceans, continuously reshaped by extreme heat. These conditions occur primarily on worlds orbiting close to their stars or possessing unusual chemical compositions. Their atmospheres interact with intense radiation, creating weather patterns sculpted by forces alien to Earth. Observing these exotic climates helps astronomers grasp the diversity of environments planets can sustain, showing that galactic weather extends beyond ordinary clouds and water storms to almost otherworldly extremes. These rains of metal and glass transform distant planets into dazzling and perilous landscapes, forged by intense heat and cosmic winds. Repeated supernova explosions carve immense cavities throughout the Milky Way. Massive stars end their lives with powerful detonations that send shock waves rippling through surrounding space, shaping interstellar gas and leaving behind vast empty voids. These stellar cataclysms are both destructive and creative, forging the structures and chemical richness of the galaxy while providing a rhythm to the ongoing life cycle of stars and planets. Over millions of years, repeated stellar explosions in the same regions can carve out enormous voids in the galaxy. These vast cavities contain far less gas and dust than their surroundings and are observed as immense bubbles shaped by overlapping shock fronts. Within them, the gas is often hot and diffuse, while their edges form denser walls where matter has been swept aside. These structures reveal the history of star formation in their neighborhoods. Massive star clusters often form together, live briefly, and explode in relatively short spans, reshaping their surroundings and influencing where the next generation of stars will emerge. Studying these voids allows astronomers to understand how energy propagates across the galaxy, showing how the Milky Way is continuously molded by cycles of creation and destruction, leaving lasting imprints in these hollow regions. Some stars do not remain bound to their home galaxies. They are cast into intergalactic space. Powerful gravitational interactions can hurl stars away entirely. When a star passes near a black hole or a tightly bound cluster, it may gain enough speed to escape completely. Once freed, it becomes a solitary wanderer drifting through the void between galaxies. These stars still shine, yet their isolation makes them incredibly difficult to detect. Their journeys can carry them far from any source of light or warmth. Throughout its long history, the Milky Way has likely ejected many such stars, some flung during collisions with other galaxies, others cast adrift when companions exploded or shifted the balance of forces. Studying these rogue intergalactic travelers helps astronomers understand the extreme events that can occur in galactic environments. They tell the story of violent forces that liberated them, silently drifting in darkness. The Milky Way also hosts ancient stellar clusters. Scattered across the galaxy, globular clusters are dense, spherical collections of stars formed when the Milky Way was young. Many are older than the Earth, the Sun, and even the planets in our solar system. They harbor some of the first generations of stars, born before the galaxy settled into its spiral form. Inside these clusters, stars move along tightly packed orbits, filling the night sky with light from within. Their chemical compositions reveal conditions in the universe long before heavy elements became widespread. Globular clusters orbit beyond the Milky Way's main disk, drifting along long paths in the galactic halo. Observing them allows scientists to reconstruct the galaxy's history and understand how its oldest structures came to be. Their age commands quiet respect. They have survived collisions, mergers, and countless cosmic events. They are ancient survivors drifting through a galaxy that has changed dramatically since they first ignited billions of years ago. Some stars in our galaxy spin like cosmic lighthouses, emitting blinding beams of radiation. Known as pulsars, these stars rotate rapidly and send out streams of radiation from their magnetic poles. As they spin, these beams sweep across space, and when aligned with Earth, we observe repeated pulses of light. The effect is reminiscent of a rotating lighthouse, but far more powerful. Pulsars form from massive stars that collapse into neutron stars after supernova explosions. Their rapid spin and intense magnetic fields make them unique among stellar remnants. Some pulsars rotate just a few times per second, while others spin hundreds of times in the same period, producing regular pulses of light. These steady rhythms help astronomers measure distances, map regions of the galaxy, and explore fundamental physics. Binary pulsars orbiting each other can even produce ripples in space-time, contributing to our understanding of gravitational waves. These cosmic beacons give the Milky Way a rhythm, sending steady signals through the darkness and allowing us to study distant regions with extraordinary precision. Even after billions of years, stars carry the story of their origins as they drift across the galaxy. Moving clusters reveal how stars migrate from their birthplaces to new regions, gradually reshaping the galactic landscape. Some groups eventually disperse so widely that they blend into the Milky Way's background population. Others endure as coherent streams, like silent caravans gliding across the cosmic expanse. Their steady motion imparts a sense of continuity to the galaxy, showing how stars carry a shared history even as they wander. The Milky Way is also home to stars that launch narrow, high-speed streams of particles into space. These stellar jets often form when matter spirals onto a dense object, such as a neutron star or a young star surrounded by a gas disk. As material falls inward, magnetic fields twist and focus the flow into slender jets that can travel light years from their source. These streams carve luminous pathways through surrounding gas, revealing the structure of their environment. In young stars, jets help clear away leftover material from the formation process. In older, more massive stars, jets can reach extraordinary energies, generating radiation detectable across the galaxy. These striking phenomena illustrate how gravity and magnetic fields collaborate to produce structures both powerful and elegant. When a star channels energy into a focused outflow, it is a reminder of how dynamic and creative the universe can be. Small systems can send ripples far beyond their immediate surroundings. Some stars move so rapidly that they may eventually leave the Milky Way entirely. Most stars follow stable orbits shaped by the galaxy's gravitational pull, yet rare groups can achieve extraordinary velocities that propel them into intergalactic space. These hypervelocity stars are often launched by intense gravitational interactions. Some are flung outward like stones from a slingshot after passing close to the central black hole, while others escape after a binary companion explodes or a sudden orbital disruption occurs. Once accelerated, these stars travel immense distances, ultimately becoming solitary wanderers in the void between galaxies. They shine like ordinary stars, yet their unusual speeds reveal a dramatic past. Studying them helps astronomers understand the extreme conditions near the galactic center and the consequences of supernova explosions. These runaway stars remind us that even the largest galaxies cannot hold all their members forever. Some escape, carrying their light into the cosmic darkness. Their journey, shaped by the moment of release, continues silently for billions of years. Certain regions of the Milky Way are filled not with cold gas, but with electrically charged plasma clouds. These clouds are composed of high-energy particles that react strongly to magnetic fields, behaving differently from ordinary gas. They can twist into filamentary shapes, ripple like waves, or glow softly where electrons spiral along magnetic structures. Many of these plasma clouds are generated by massive stars or supernova explosions that inject energy into their surroundings, while others are sculpted by turbulence in the interstellar medium. Studying these regions provides direct insight into the invisible magnetic environment of the galaxy. By tracing these plasma structures, astronomers can map the otherwise unseen forces that shape the Milky Way. Cosmic rays, as they travel through the galaxy, are guided and deflected by the surrounding magnetic fields and charged regions. These interactions add another layer of complexity to the Milky Way, revealing that the spaces between stars are far from empty, filled instead with subtle streams of energy shaped by matter and magnetic forces. Across the Milky Way, vast clouds glow with the vivid colors created by energetic young stars. These stars flood the surrounding gas with ultraviolet light, causing it to shine. Hydrogen emits soft reds, while oxygen can produce gentle greens or blues. These glowing regions are often nurseries for new stars, where dense pockets of gas collapse to form young suns. The shapes of the clouds are sculpted by stellar winds, radiation, and turbulence, giving rise to pillars, gaps, and filaments that are among the galaxy's most striking structures. Studying these clouds helps astronomers understand both how stars form and how they influence their environment. Their colors also provide clues about the chemical composition of the galaxy, revealing the energy and beauty inherent in stellar creation. In some parts of the Milky Way, there exist brown dwarfs that never fully ignite into stars. These objects fill the quiet space between planets and stars. Formed when collapsing gas clouds fail to gain enough mass to trigger nuclear fusion, they shine only faintly, often primarily in the infrared, remaining hidden from the naked eye. Brown dwarfs occupy the spaces between brighter stars, adding a subtle layer of complexity to the galaxy. Their atmospheres host unusual molecules shaped by low temperatures and high pressures, and some exhibit dynamic weather patterns that change over hours or days. While they never blaze like true stars, brown dwarfs play an essential role in the galactic population, quietly weaving complexity into the Milky Way's structure and providing astronomers insight into the lower limits of star formation. Some worlds within the Milky Way are entirely covered in molten lava oceans. Orbiting extremely close to their stars, their surfaces melt into flowing seas of incandescent rock. The intense heat prevents the formation of a solid crust, and instead, their surfaces are reshaped continuously by gravity-driven flows and atmospheric winds. Temperatures rise above the melting points of many minerals, turning their landscapes into vibrant reds and oranges. On certain planets, tidal forces from their stars further heat the interior, stirring the lava oceans and intensifying surface dynamics. These extreme environments highlight the diversity of the Milky Way and the powerful influence stars exert on their planets. Each glowing nebula, drifting brown dwarf, and molten world tells a unique story, revealing the hidden complexity and vibrant life of our galaxy. As a result, volcanic activity can sustain self-renewing oceans of molten lava, continually reshaping a planet's surface. Studying these extreme worlds helps astronomers understand how planets evolve under intense radiation. Their atmospheres may contain vaporized rock that condenses into mineral clouds. As these clouds cool, they can fall back onto the molten surface as unusual forms of precipitation. Lava-covered planets reveal that planetary environments in the Milky Way extend far beyond anything seen on Earth, offering a glimpse into cosmic landscapes sculpted by heat and motion under the harshest conditions. Across the galaxy, pulsars rotate with the precision of cosmic timekeepers. These rapidly spinning neutron stars emit beams of radiation from their magnetic poles. Each time a beam sweeps past Earth, it produces a pulse of light with remarkable regularity. Some pulsars maintain timing so consistently that they rival atomic clocks, making them invaluable tools for probing the Milky Way. By observing subtle variations in pulsar timing, astronomers can detect the influence of passing objects, gravitational waves, or internal stellar dynamics. A pulsar's spin is a remnant of its progenitor star. When a massive star collapses, its core contracts, causing it to spin faster, similar to a figure skater pulling in their arms. Although pulsars gradually slow over millions of years, early in their lives, they can rotate hundreds of times per second. Their intense magnetic fields channel charged particles along narrow paths, producing the distinctive beams that make them so extraordinary. Pulsars act as natural laboratories for extreme physics, revealing how matter behaves under conditions far beyond any terrestrial experiment. In certain regions of the Milky Way, enormous reservoirs of molecular gas exist. These dense, cold clouds are rich in the ingredients necessary for star formation. Yet the galactic center is far from tranquil. Strong radiation fields, turbulent motions, and extreme gravity constantly influence the gas. As clouds orbit near the central black hole, they stretch, compress, and heat, yet dense pockets remain shielded enough for molecules to survive. These regions host some of the galaxy's most massive and active star-forming areas. Observing them requires radio and infrared wavelengths which can penetrate the thick dust surrounding the core. Mapping the distribution of this molecular gas helps astronomers understand how stars can form under extreme conditions and reveals how energy from the galactic center shapes the evolution of nearby regions. These hidden gas reservoirs are critical for the birth of new stellar generations, showing that even the most intense environments can provide fertile ground for creation. There are also double planet systems that orbit each other like cosmic dance partners. Not all orbital motions revolve solely around a star. In rare cases, two planets of similar mass form close enough to share a common orbit. Instead of one dominating the other, the pair revolves around a shared center of gravity between them. These binary planet systems move like a slow, elegant dance through space. Their mutual motion influences their rotation, tidal interactions, and long-term stability.